Hi, I'm Mike Rowan, and this is part 3 of the Retro Tinker Game Master Cartridge, Creating Sound from Extended Color Basic. The emphasis of part 3 will be the noise channel of the SN76489. So what is the noise channel? In general terms, it generates different forms of white noise. In music, that could be used to create drum sounds, cymbal sounds. In games, it can create sounds like an engine or a rocket or explosions. In part 2, we discussed the tone channels, channels 0, 1, and 2. They each have a 4-bit volume register and a 10-bit tone register. The tone registers are pretty straightforward. You control the frequency of a tone by writing values to the 10-bit tone register. The noise channel works a little bit differently. Like the tone register, there is a 4-bit volume register, and it works just the way it did in all the other channels. However, instead of a 10-bit tone register, there's a 3-bit control register. The 3 bits of the control register are broken into 2 different fields. Bit 2 selects the type of noise. A value of 0 selects what's called periodic noise mode, and a value of 1 selects white noise. And rather than diving into the physics of noise types, just note that these are 2 different algorithms on the chip. They each have a unique sound, and we will cover both of them in the video. Bits 1 and 0 control the shift rate. Well, what's the shift rate? It determines by how much the input clock signal is divided before it enters the noise generator. Again, just think of this as setting a mode for the noise generator, and each one sounds unique. Since this is a 2-bit value, we can only select 4 different modes. 0, 0, 1 for 1, 1, 0 for 2, and 1, 1 for 3. The first 3 values, 0, 1, and 2, are fixed shift rates. So it's easiest to think of those modes as being low, medium, and high. Let's take a look at a table. So with a shift rate of 0, we get a low shift rate. 0, 1 would provide a medium shift rate. And 1, 0, or decimal 2, will give you a high shift rate. When you hear the difference between these modes, it's much like shifting octaves on a piano. The first 3 shift rates are derived from the clock signal being fed into the sound chip. In other words, the clock that's on board. Let's take a look at these first 3 modes on the color computer so you can better understand what these shift rates sound like. Now we're going to run a demo program on the color computer, and here we're setting the noise channel 3 to low mode, so we're writing 100 to the control register, and this is what it sounds like. Next, we'll set the control register to be 101 to give us medium noise, and this is what it sounds like. And finally, we'll set the control register to be 110 to give us the high noise mode. Now we'll cycle through low, so you can hear that again, medium, and finally high again. And now we'll just cycle through them so you can hear the differences. Now we'll run the same example using periodic noise instead of white noise. It's not going to be as impressive. Periodic noise works best when tone 2 mode that we'll cover here in the future. Okay, now we're going to set it to medium. And then finally we'll set it to high. So this is periodic noise in the high mode. So we've covered the first 3 shift rates and understand the low, medium, high modes for both periodic and white noise. That provides 6 different sounds. The mode that I haven't covered yet is the shift rate of 1-1 or decimal 3. This is known as tone 2 mode, and we will get into it. But before we do, let's see how we write to this register with a latch byte. As you recall, bit 7 is a 1 denoting a latch byte. Bits 5 and 6 are the channel bits, and these will be 1-1 for channel 3, which is the noise channel. Bit 4 selects which register we want to send to. If bit 4 is a 1, we will write to the volume register. So the remaining 4 bits will be written to the volume register. Now let's look at writing to the control register. Bit 7 is a 1 for a latch byte. Bits 5 and 6 are the channel bits, so 1, 1 for channel 3. This time, bit 4 will be a 0 to select the control register. There are 4 data bits in the latch byte, but because the control register is only 3 bits, bit 3 will be ignored, and only the last 3 bits are written to the register. You can still use data bytes to write to the control register after a latch byte. Bit 7 would be a 0 to denote a data byte. Bit 6 is always ignored in a data byte, and there are 6 data bits. But again, because the control register is only 3 bits wide, bits 3, 4, and 5 are also ignored. So the last 3 bits are the bits that are written to the control register. Let's walk through creating a latch byte to set the 3-bit control register and see what value we come up with to write to address FF41. Let's use the type of 1 for white noise, and we're going to select a shift rate of 10, that's decimal 2, to select the high shift rate. So we want to write 110 to the 3-bit control register. So to create the latch byte, bit 7 will be a 1 to denote that it's a latch byte. Bits 5 and 6 are the channel bits, so click 11 decimal 3 for the noise channel. Bit 4 will be 0 to direct the data to the control register. And the 4 final bits are data. Bit 3 is ignored because only the last 3 bits will fit into the 3-bit control register. So we'll set a value of 0110 as the last 4 bits of the latch byte. And when we convert this value to decimal, we get a value of 228 or E4 in hexadecimal. So writing 228 to address FF41 would write 110 to the 3-bit control register. We've looked at the fixed, low, medium, and high shift rates, but I waited to talk about the value of 3 or binary 11 in the shift rate bits. This mode is called tone 2. In this mode, the frequency of tone channel 2 controls the noise being generated from noise channel 3. To get a little better idea of what I mean, let's look at a logical diagram of the noise and tone generators inside of the sound chip. The onboard oscillator generates an input clock to the sound chip. This is fed to all 4 of the sound channels. The 3 tone channels use 10-bit values to divide the clock to generate different output frequencies. The noise channel uses the same clock, but the 2 shift rate bits only allow the input frequency to be divided by 3 fixed rates. That's what provides the low, medium, and high modes. But in tone 2 mode, rather than using the fixed clock signal as input, it instead uses the tone frequency generated by tone channel 2. What this means is that you can control the input frequency to the noise generator with tone channel 2's 10-bit tone register. 10 bits allows for 1024 different frequencies into the noise generator. So this mode allows you to generate a much wider variation in noise by simply changing the 10-bit tone register for tone channel 2. Let's look at this again from the control register point of view. When the shift rate is set to 00 or 01 or 10, that's our low, medium, or high, the frequency sent through the noise generator is derived from divisions of a fixed clock frequency. So low, medium, and high are just dividing the same input frequency, each by a different amount. However, when the shift rate is set to tone 2 mode with binary 11, The noise generator uses the frequency output of tone channel 2 instead of the fixed clock frequency. So this mode ties the output of channel 2 to the input of the noise generator and allows you to control the noise generator through channel 2's 10-bit tone register. In tone 2 mode, the value written to channel 2's tone register will change the noise output of channel 3. Just think of this mode as tying channel 3 to channel 2. Let's take a look at this on the color computer. Alright, now we're going to do a demonstration on the color computer of tone 2 mode. So to enable that, we're going to enable it with white noise. We're going to send the LATCH byte out to populate the control register. So let's look at the binary here. In decimal it's 231. In binary we have 1 for LATCH byte, 1 for channel 3, the noise channel, 0 to write to the control register, and then the last 4 bits, bit 3 is ignored, so we just leaves us with 111. The first one is for white noise mode, and then 11 we'll put it in tone 2 mode. So because we're using tone 2 mode, we need to set the 10-bit tone register for tone 2 so we can manipulate the output of the noise channel. So first we'll need to send a LATCH byte. LATCH byte would be 1 for LATCH byte, 10 for channel 2, and then we'll send zeros to set the lower 4 bits to 0. Then we'll send another data byte so that we can set the upper 6 bits to be 0 as well. So that gives us our total of 10 bits. So now what we're going to do is we're going to cycle that register from 0 up to 1024 so you can hear what the sound is out of the noise channel. Here we go. Now we'll run the same example, except we're going to select periodic noise. So instead of 111 in the control register, it'll be 011. So we'll send our LATCH byte, 1 for LATCH byte, 11 for channel 3, 0 for control register, and then the last 3 bits 011. And then we'll cycle from 0 to 1024 again, except for periodic noise. Here it is. Alright, now we're going to do that again, except we're going to turn up the volume on tone channel 2, so you'll be able to hear channel 2 and 3 at the same time. So as the frequency increases, you will hear its impact on the noise channel. Okay, we're going to look at the loop that I wrote to cycle through these values, 0 through 1024, because we have to send a LATCH byte and a data byte every time we populate that 10-bit register. So for the lower bits, we've got 4 bits, so we go from 0 to 15. And then for the upper bits, we have 6 bits, so that gives us the values of 0 through 63. So when we create this is the code from the program, we create 2 for loops. Value of x will be for the upper parts and y will be for the lower parts. And then we alternate poking the LATCH byte followed by the data byte. So we cycle through 0 through 15, then increment x, and do that again and again, and that's how we do it in the code. Well, as you can see, the SN76489 can generate a broad range of noise signals. And you should experiment with cycling shift rates, noise types, and volume to create even more complex outputs. And hopefully these videos have helped you to understand the underlying principles of controlling the SN76489 that's aboard the Game Master cartridge. In the next video, we'll begin to explore the bank-switched ROM capabilities of the Game Master cartridge. Until then, long live the color computer, and I'll see you in the next video.